John Hughes, candidate for the Bachelor of Science degree in Electrical Engineering. Started working with John in the summer of 2012 in the lab rehabilitation effort. So over many months of very hard work, John worked with Dinesh to restore lab space and redefine some of the lab equipment and material, and to create inventory for labs. In 2013, I started working with John on earthquake forecasting and supporting efforts to develop advanced laboratory material, particularly for electronics. So as the main student in charge of developing codes for earthquake forecasting, John has developed a good understanding of earthquakes, the ionosphere and its parameters, and how they relate to earthquake forecasting. The work he's done for his senior thesis is quite exceptional in my view, because he's been able to treat GPS data in such a way that they can become error-free and be used to show correlation with seismic activities. John has shown great promise as a future research engineer, and my hope that he will continue to remain curious about scientific endeavors long after he enters the workforce. So this is with great pleasure that I welcome John Hughes to the thesis analysis.
Okay, I'm going to present my senior thesis on using global positioning system data to find a potential correlation with seismic activity. So, my overview of my slides, I'm going to be talking about global positioning satellite data processing, purpose of my research, and talk about GPS and total electron content, earthquakes in TEC, Japan earthquake, and I have a video clip of the Japan TEC with earthquake. So, yeah. So GPS data is used to estimate someone's position on Earth. It's also used to estimate TEC, otherwise known as total electron content. Total electron TEC is the number of free electrons along the line between the receiver and the satellite. The picture below shows the number of electrons within a cylinder, which is the approximation of the TEC as shown in the formula below. So, GPS is corrupted by a various of errors. These errors affect the satellite positions, and these errors are from the receiver positions, and there's also errors from the atmosphere. So, in order for GPS data to be useful, we need to remove all the errors. Only a few groups in the world have done that. The purpose of this research is to use a baseline code developed by a group in China, and to expand as well as to adapt this code to remove all the errors and compute the TEC. So in order to talk about how I remove the errors in the GPS data, I want to talk about GPS data processing. So GPS data is stored in a file called the RENX file. This file contains pseudo range, or the position information at two different frequencies. This file also contains the phase information for these frequencies as well. Besides the information in RENX files, I also use other files called Ionics and SP3. Both of these are used to correct errors due to the satellite's position. Then I use the code developed by the China group to remove these errors. So basically, my primary goal is to start with for our GPS data, then use that data to remove all the errors. Then when I have the corrected GPS data, I then use that to compute the Japan total electron content. Then after when I did that, I have to find a potential correlation with TEC fluctuations and seismic activity. So these are to compute TEC from position information provided by GPS. I started with equation 1. Then I solve for for TEC using equation 1 as shown in equation 2. I've been talking about TEC data, but I have not told you why I'm interested in TEC data. So what is the correlation between TEC data and earthquakes? So to talk about this connection, let's first briefly discuss what earthquakes are. There are 3 types of earthquakes. In the divergent type plates are moving away from each other. In the convergent type, plates are moving toward each other, and in the transformed type, plates are sliding along each other. So, in the Japan earthquake was a convergent type. My hypothesis was that as the plate moves than typically expected, they'll create seismic activities, which result in earthquakes. In addition, as the earthquakes occur, they create free positive charges. These 3 positive charges travel upward to the ionosphere and create ionospheric disturbances. The plan is to see if we can usually observe these disturbances. So, in order to see if we can observe these disturbances, I've used the following data processing method. We took the GPS data, we remove all the errors from it, then we convert that GPS data to TEC data, and then we display it. So, to test the GPS data processing, I've looked at sets of trial data. One set of these data is from a group of receivers in Europe and a quiet ionosphere time as shown in figure 1. The TEC in figure 1 is very smooth. And then the second set of data that I use is from Japan. In figure 2, we show that the distribution of receivers over Japan are they're basically the red dots in figure 2. We picked that data from one of the receivers around the time of the earthquake. These results are shown in figure 3. We can clearly see the fluctuations in the Japan TEC data. Now let's look at the Japan earthquake in more detail. On March 11, 2011, a magnitude of 9.0 earthquake took place in Japan. The epicenter of this earthquake was located at 442.36 longitude and 38.32 latitude. This earthquake also occurred underwater. So, now what I've done is to look at the data from about 90 receivers around the time of the Japan earthquake. I wanted to see if there will be any disturbances in the TEC. The picture you are looking at explains what I'm going to display. You would see TEC image which varies with time. There will be 3 primary colors in the TEC image: red, yellow, and blue. Red indicates a large amount of TEC, yellow indicates less TEC, and blue indicates almost no TEC. We want to watch carefully to see how the colors fluctuate around the time of the earthquake. So, the blue dot on the right hand side it's basically that dot right there, is the epicenter of the earthquake. Right here is the axis for the movie: azimuth angle and elevation angle. These are the longitude and latitude for this video clip. So the TEC image represents the number of free electrons per meter square in the particular locations as time varies. What you see is as the earthquake approaches, there will be a lot of fluctuations in the TEC. More specifically, you will see that areas that are most affected by these fluctuations are close to the epicenter. So now I'm going to play my video clip. It is, I believe, 2 hours, because right now you see that GST, that stands for Japan Standard Time, and since we all know that it's going to be like 1 o'clock or 1:30, it's taking place in hours and not in minutes.
Sense of how much area we're talking about here? Is this like most of the main island of Japan, or is it
Japan has a lot of receivers. On my earlier slide, I had red dots and blue dots.
Yes.
The red dots represents the receivers that I actually used to create this movie.
Okay.
So now, wrapping up my conclusions, I basically showed how errors can be removed from the GPS data. I also showed how to compute the TEC data from error-free GPS data. I also showed that the TEC data is correlated with seismic activities for the Japan earthquake, and these results clearly show that the earthquake is approaching under very severe TEC fluctuations that take place. So I would like to thank Dr. Conley for helping me with my project and with my PowerPoint presentation. I would also like to thank the group from China for letting me to use and modify their code. I'd also like to thank Dr. Free for his overall support. And I'd also like to thank many of my friends and colleagues who supported me last year through some very difficult times. And that's it. Any questions?
Questions for John?
Yeah?
I mean, I guess for people in the room, I don't know if you could explain like the video.
Explain the video?
Yeah.
Well, what are we seeing there?
Yeah,
What?
the difference.
Oh.
How it affects.
What? So,
You can speak over it as explained.
okay. What you'll see right here is this color bar right here. This is basically the value for the total electron content over here. You'll notice that it stays around in this region right here, like yellowish, which then it goes somewhere up here, and then it goes somewhere down here, like after the earthquake, but it takes it like several hours before you actually see that process.
Also explain that the time.
The time?
When the earthquake is approaching.
Yes,
the
you'll
right-hand side, it's
see the time.
Until the earthquake is about 2 hours 26 minutes.
Yeah, and then the Japan Standard Time is right there. So is that good enough explanation for you, or?
So the suggestion is if we could see this happening ahead of time,
Yes, if we could see
what's
it.
about to happen.
Yeah, but I didn't take data of Japan data like without seismic activity, so I don't know what the normal color would be for that. But what I showed so far is that there is some fluctuations with the total electron content because of seismic activity, but I haven't got data with in Japan without seismic activity though.
You forgot you looked at this data, John.
What?
So you forgot. But one thing, yeah, we looked at tons of that data.
Yeah.
So one thing that's significant here, first where the depletion is taking place. You see that big blue that's facing the epicenter? That's a jump. That's a 55 unit jump in less than half an hour. Okay? So you're going from red down to blue in about 30 minutes. Impossible with the normal atmosphere. It's just too smooth, like smooth. It's not gonna go That is something causing it. Right? Now people can make argument that there's something else causing it, but there's something causing it.
Something, yes.
Right.
So that was a depiction of the atmosphere of the total electron content in the atmosphere of Japan. Like the main island.
Or you mean the whole entire island, or just a portion?
That's the atmosphere of Japan you're measuring, right?
In
In the picture.
the picture,
In the video.
It's a small area.
it's a small,
Go back to this to that 3D picture that's showing this
but
I guess I'm just wondering how much.
right there.
right there. See, I plotted in MATLAB all the receiver locations in Japan. That is, it's basically the blue dots, while the red dots you see right here is the area that I use for my code when I actually run my video clip. It's actually plotting those points right there. So any more questions?
Did you say you don't have any data far from the
See, I didn't take
core way out?
I didn't take data for Japan over, before the earthquake. The only time that I actually did it with normal ionic sphere conditions was when I was testing the code with European sites. So I haven't used any Japan data for.
When you were testing it for the European sites, was it in the yellow-green sort of area all the time? Or?
See, for that part, I was just using their sites to understand their code and remove all the errors. I haven't gotten to the point where I got the display working yet. And when I was at that point, I had to use Japan files, so I didn't have the opportunity to actually create a movie for that.
So let's go to the previous slide. That may help. I think some of the questions being asked here. Good question for you. So if you look at this slide where you picked up what's this grass? Is that
Grass.
something? Picked up a receiver grass somewhere, and this is the TEC for that. And move it, so you can see TEC is telling you what you should expect, right? You have high value when you far away because you're going through a lot of atmosphere, and as you come close, you get less and less atmosphere, then you move away again, which is kind of what the GPS is like. So that's, and it's smooth. So you go to the next slide.
Next slide, you could see
Do you remember which receiver you picked up here?
that's 0001.
What is that?
See, Japan receivers, they actually use numbers instead of names.
So could be anywhere in the dots here. What you can do is the same behavior.
Yeah, I'm trying to find out where the baseline is for your color bar.
Right. Right.
And do you subtract a baseline? Do you find an area where
Well-
there's no activity and subtract the baseline, or?
No, there's no baseline here because he's removed the errors. I think Joe did that kind of baseline thing. He's removed all the errors. He's just displaying what the TC is looking at.
But there is some baseline for the TC
So
versus
it would
time.
be, like for example, I would take in that case, if without any activity, it will do something like this. You wouldn't have this. You wouldn't have these jumps here. That's what I think would happen. I'm just But
Would it be better to subtract some kind of baseline
yeah,
or something
absolutely.
like
I think it
that?
probably would be some to subtract and just show the disturbance. Yeah, sure.
So, any more questions, or is that it?
You went to janitor.
Softball, don't worry. So last summer, when I heard you speaking on your preliminary work, you were still working on removing the errors from all the receivers.
Yes.
So you're using that code from China. So in removing the errors, are you essentially coming up with a whole new code that's just now out there that anyone can use? Is that how this works?
For that, I had to modify some of their code to get it to work for Japan files, but that was a small change, and I didn't change too much of their code. I only had to convert their pseudo-range measurements into total electron content. But after that, it was just, yeah. So is that it?
Okay, I think you had enough.
I don't know.
Okay, so thank you all for coming. This will be our last session for this year. So we come back again next year.